Welcome back, guys. In this video, we're continuing our studies of relative extrema, or extrema in general, and this time we're talking about finding relative extrema. Remember, that's a relative minimum or relative maximum. That's the smallest y value in a neighborhood or the largest y value in a neighborhood, and we're going to find those using a test called the first derivative test. And before we do that, we're going to define the terms increasing and decreasing, and then we'll state the test, and then we'll apply the test to a couple of problems. Now, everything that I've written here on the top right is basically a problem statement. Like these are the types of things that you might be asked in this section. Somebody might ask you to find the open intervals where the function is increasing or decreasing. And they might also ask you to apply the first derivative test to identify all relative extrema. So that's basically what we're going to do. Now, first we need to define the terms increasing and decreasing. Now, we say that a function is increasing on an interval I. So that might be an interval from A to B, let's say. If x1 being less than x2 implies that f of x1 is less than f of x2 for all x1 and x2 and I. So let's think about what this means. It's probably exactly what you would expect, but let's talk about how these symbols mean exactly what you would expect. So let's say we've got a function on an interval, and our interval I looks like this. Maybe the interval I starts at x equals a, and maybe it ends at x equals b. Well, this particular function, the one that I just drew, is increasing on the interval from a to b. I is just the interval from a to b. Whoops. And we can see that just by looking at the graph. Now what this says is, if this is true, then this is true. So if x1 is less than x2, so x1 and x2 are just a couple of numbers. They're on the interval from a to b, but x1 is to the left of x2. If x1 is less than x2, well, that implies that this y value, the y value at x1, is smaller than the y value that corresponds to x2. So there's f of x1, and there's f of x2. So we see that a function's increasing. I think it's easiest to think of it this way. If you look at the graph from left to right, and the y values are going up the whole time. Now, we talk about functions being increasing on an interval. So when they ask you where it's increasing, they're actually asking for x values. But we say the function is increasing if you look at that function on the interval from left to right, and the y values are going up. Now, if you're saying to yourself, but Ms. Townsend, the y values are going down if I go this way, you're absolutely right. But whenever we're examining a function, we define increasing and decreasing in terms of looking at the graph from left to right. So as x increases, what happens to the y values? Now, this statement says that as long as x1 is less than x2, so this one is to the left of this one, the y value over here is less than the y value over here. And if that's true for all x1 and x2 on that interval, well, then we're going to get a pattern like this. It's true for this x1 and this x2. It's true for this x1 and that x2 and this x1 and that x2. No matter what I do, as long as this one is larger than this one, the y value over here is larger than the y value over here. Or the y value over here is smaller than the y value over there. When I look at it from left to right, the y values are going up for all x1, x2 on this interval. So we say that the function is increasing on an interval if it sort of looks like that. Now we say a function is decreasing on an interval if it maybe looks like this. You can probably guess. Now in symbols, this is the way it looks. This is the way we typically write it, but let's think about what this means. This again says that if x1 is less than x2, and x1 and x2 are on the interval I, so you just pick any x1 and you pick an x2 to the left of it. I said left, to the right of it. And you look at the y values. This says that the function's decreasing if you can do that, pick an x over here and then pick an x value to the right of it, and then look at the corresponding y values. If the y values are going down as you go from left to right, so x1 less than x2 implies that f of x1 is larger than f of x2, so the y's are decreasing while the x's are increasing, then we say that the function is decreasing on I. So when we refer to increasing and decreasing, we're always talking about the y values. Are the y's going up? It's increasing. Are the y's going down? It's decreasing. But be careful. When someone asks you for the intervals, the open intervals, where a function is increasing and decreasing, they're always asking for a location. They're saying, where is that happening? At what x values are all the y values going up? Or at what x values are all the y values going down? So we're looking at the y values and seeing whether they go up or down. But when I ask you where's the function increasing or decreasing, I'm asking for location. That's about x values. So let me make that a little bit more concrete by showing you a picture. Let's say our function looks like this. Maybe at x equals 1, something that looks like that, and then at x equals 4, we get this point, and then maybe at x equals 6, we have a zero slope again, and then it just keeps going. Okay. Now someone might ask you, okay, here's a graph, y equals f of x. Where is the function increasing and where is the function decreasing? Or, in other words, find the open intervals on which the function is increasing or decreasing. So they just show you this graph, they show you a picture. And they just say, tell me where the function's increasing or decreasing. And we assume the trends continue. That's what those arrows mean. Well, the function's increasing on all of the intervals, where when I look at the graph from left to right, the y values are going up. That's where it's increasing. I'm going to highlight all the intervals where the function is increasing. So as I'm looking at the graph, I start over here and I start graphing it. Like I just imagine that I'm tracing this graph myself. Well, I can see that as I go from left to right, the y values are going up over here. So it looks like they're going up until a little bit more than 1 actually, maybe there, and then they start to go down. So the function is increasing until I get to whatever that point is right there. And then it's decreasing for a while, we'll skip that, and then we ask for when is it increasing again? Well, it looks like it's increasing here and then increasing there. So it's increasing there, and then it's increasing over there. So where is it increasing? On the orange part. Now that's not an acceptable answer. You can't just say on the orange part. When somebody asks you to find the open intervals where the function is increasing or decreasing, they're asking for the x values where the y values are going up. So they're asking for intervals of x values. They said find the open intervals, so we don't want to include the endpoints. Well, this function is increasing, starting over here, and we're reading this from left to right, and we're thinking about x values. So remember, this is a number line for x. It goes from negative infinity to positive infinity. So over here, the y values are going up. The y values are going up, so it's increasing, but you say, well, what is the interval of x values that's associated with that? Well, it looks like the x's go from negative infinity, and the y's keep going up, and the y's keep going up, and the y's keep going up, until we get to this x value, whatever that is. I'll call that, say, 1.4. So I'll say this function is increasing on the interval, and we're reading it from left to right, from negative infinity to 1.4. And then it goes down for a while. And then over here at x equals 4, say, hey, it starts going up again. Now maybe it's the case that when x equals 4, y equals, let's say 1. That's what it looks like with my scale, right? The y value does not matter. If somebody asks you for the intervals where the function is increasing, well, you need to look at the y's and make sure they're going up. They are. And then you have to think about what are the x values that go with those y values. So the y values start going up at x equals 4. And then they continue to go up until x equals 6. And it looks like we might have 0 slope, or maybe maybe it's not even a 0 slope from the way I've drawn it, and just keeps going. So it goes from 4 to infinity. Okay, so our function's increasing there. And then the question might also say, okay, where's the function decreasing? Well, obviously it's decreasing from there to there. And again, we're looking for an interval of x values. So f was increasing on these two intervals. Now, that might be enough. You might just stop there. Now, some software programs, instead of just saying this interval and this interval, they might have a union there. They might say the union of this and this. It doesn't really matter to me. Either one is fine. As you're doing quizzes in this class, you'll have to figure out what WebAssign likes. There's going to be a certain preference in their notation. Okay, so f is increasing here and over here, and it's decreasing here. And again, we're looking for intervals of x values. So f is decreasing on the interval from here to there. And the x value that goes with that is 1.4, and the x value that goes with that y value is 4. So this is decreasing on 1.4 to 4. And those are the open intervals. We don't include the endpoints. And if you're saying to yourself, why don't we include the endpoints? It's a very good question. And the reason we don't include the endpoints is because we tend to think of this point at the top or this point at the bottom as a place where it's neither increasing nor decreasing. It's increasing until it gets to there, and then it's decreasing on the next interval. So what is it doing at the top? Like, it can't be both. I guess we're saying that it can't be both, so we're not going to include those on our interval. Now, if we have a picture, it's obvious. You can just look at the picture and identify the intervals or the functions increasing or decreasing by looking at the y values. But what if we didn't have a picture? What if all we had was an equation? Somebody says f of x is equal to this, and you want to know, what does it look like? Where is it increasing? Where is it decreasing? Well, one thing we can do to find out where it's increasing or decreasing is look at the derivative. Now notice, if I drew a bunch of tangent lines over here, let me get a straight edge, also known as a sticky note. So I've got my sticky note, my straight edge. It's playing the role of my tangent line. Okay, look. If I draw a tangent line there, as you look at it from left to right, you see it's sloping up. It has a positive slope. If I draw a tangent line, say at this x value, try to draw a tangent to the curve with the same slope as the curve, it's also sloping up. And that's true for all of the x values until we get to right about there. And then at the top, according to my picture at x equals 1.4, we've got a 0 slope at the very top. But it's been increasing the whole time. We've got a positive slope and a positive slope and a less positive slope. If you're saying, what do you mean less? It just means less steep. You think about climbing a mountain. If it's very, very steep, you don't want to climb that, that's a large slope. You know, if the mountain looks like this, you're like, hey, that's not so bad. It's like a set of stairs that's easy to climb. But I mean, it has a positive slope, it's just not as steep as something like this. Like, I don't want to do that. I don't mind doing that. So we've got all of these positive slopes until we get here. And then over here where it's decreasing, if I draw tangent lines, what do you notice about those slopes? Slope is negative there. Slope is even more negative there. even more negative there, and so on. All the slopes are negative from here to here. And then over here, I start drawing tangent lines and they start being positive again. And again, how am I distinguishing that? I'm looking at my piece of paper, I'm looking at this straight edge as a tangent line, and I'm saying, wow, look, as I look at it from left to right, it goes up, so it's a positive slope. Or over here, I'm saying, look, if I make that tangent to the curve at that x value, I look at that line from left to right, it's going down, so it's a negative slope. So we've got positive slopes here, negative slopes here, positive slopes, then I tried to draw something that was close to 0, but I think unsuccessfully. Maybe it's a tiny positive slope, and then it keeps going. So what does that mean? Well, we say that f is increasing on an interval when this is true. Another thing that we can say is that f is increasing on an interval when f prime of x is positive on that interval. I'm not going to prove it, but we can easily prove it using the definition of the derivative in these inequalities. There's actually a very short proof in your book if you want to check that out. But I think intuitively it makes sense. What we're saying is f is increasing if all the slopes are positive. Well, yeah, look at the side where we've got it's an increasing graph. All those slopes are positive. And then we've got a 0 slope at the top, and then it's a negative slope on the other side. Negative slope, what does that mean? It means the derivative is negative. So f is decreasing on an interval when the derivative is negative. So this is one definition, but now that we know calculus, we've got this other definition, which is pretty sweet. It allows us to determine whether that function is increasing or decreasing pretty easily. All we have to do is find the derivative and see where the derivative is positive and where the derivative is negative. So if somebody asks you to find the open intervals where the function is increasing or decreasing, they're basically saying, find the open intervals where the function's derivative is positive, that's where it's increasing. Or find the open intervals where the function's derivative is negative, that's where it's decreasing. Okay. And then to figure out where it goes from positive to negative, like you're going to have to set the derivative equal to 0. Hey, and we've done that before when we found critical points in the last section, right? Our slopes are all positive, our derivatives are all positive here, then we've got 0 slope at the top and then negative slope. And then I go from negative slopes on this side, so it's decreasing, to 0 slope, then to positive slopes on this side. And then it looks like I went positive and I was trying to make a 0 slope, but it didn't work out. And then positive slope again. Now, everywhere where I have a 0 derivative, like that would correspond to a critical value. And I drew those tangent lines in because we've got a horizontal tangent line every time the derivative is 0. The graph has 0 slope. Derivative and slope are the same thing. Okay, so yeah, if I want to know where the function's increasing or decreasing, I just need to figure out where f prime is positive, that's where it's increasing, and where f prime is negative, that's where it's decreasing. And we're asking for the interval of x values where that's true. Now, if I'm trying to find relative extrema, well, I think we can just look at the graph and see what happens if the function goes from increasing to decreasing. It goes from increasing to having a 0 slope to decreasing, you've got a max up there. Or what if it goes from decreasing to 0 slope to increasing? Well, then you've got a min. Or, remember, increasing means positive derivative. So this is f prime is positive, f prime is 0, f prime is negative. F prime is 0, f prime is positive. So if f prime goes from positive on this side, so it means it's increasing, to 0 and then to negative, we get a max. Or if f prime goes from negative to 0, then to positive, we get a min. Now, it doesn't even have to have a 0 slope there. We could also have something that looks like this. This would work as well. Well, on that side of that graph, let's see, that's our graph now for another example. Let's say that's x equals 5. Over here, from negative infinity to 5, that interval of x values, So from on this side of the graph, our function is decreasing. And if our function is decreasing, we've got negative derivatives. If you're not sure, draw a little tangent line. You're like, look at that tangent line. As I look at it from left to right, it's sloping down. So it's a negative derivative. Negative derivative, negative derivative for all the x values. Something weird happens at 5 though. We've got that sharp corner. So it's decreasing on this side, which means the derivative is negative on this side, and it's increasing on this side, and it's increasing where the derivative is positive. If we draw our little tangent lines, we can see that the tangent lines are going up. They're sloping up as you look at them from left to right. The graphs look like this. They have positive slope. These graphs, those lines, have negative slope. So if the function goes from decreasing to having an undefined slope, sharp corner, to increasing, we get a minimum. Well, it's kind of the same thing that happened here. It went from decreasing to 0 slope to increasing, or negative first derivative to 0 first derivative to positive first derivative, or this is decreasing. So the first derivative is negative. So the derivative tells you the slope. The derivative is negative when it's decreasing. And then over here, it's increasing, so this derivative is positive. So it goes from decreasing to non-existent slope, can't take it, can't find it, it's not possible, to increasing. But it goes decreasing to increasing, we've got a min. Decreasing to increasing, we've got a min. And how can we tell if something's decreasing or increasing without the graph, without seeing this picture? You could prove this every time, which is possible, or you could just use the derivative. Now that we know the derivative, now that we know how to compute derivatives, we can use that. So this idea that I've been talking about can be summarized in what's called the first derivative test. Here it is, down here at the bottom of the page. All right. So this says, let C be a critical number of f. And remember, what are critical numbers? That's an x value for which the derivative is 0. So it's an x value C for which f prime of C is 0, so you've got 0 slope, or f prime of C is undefined or does not exist, however you prefer to look at that. So it's a critical point. It's either a flat spot on a graph or a place where the derivative is undefined. And I guess we should also point out this x value that we're talking about, it has to be in the domain. So I guess I need to say, actually I put a little arrow there. This is an x value in the domain of f, for which the derivative is 0 or the derivative is undefined. So you've got a flat spot or a sharp corner. Well, and then here's our first derivative test. I actually don't have this memorized at all. If you're saying, you're cheating, Miss Townsend, are you asking us to memorize something you don't have memorized? No, what I have memorized is this. I understand increasing and decreasing and how it works. Every time I want to use the first derivative test, I draw a picture. So this says, we're at a critical point C. So this is an x value where the derivative is 0 or undefined. If f prime changes from negative to positive at x equals C, so f prime is going from decreasing on one side to increasing on the other, then we have a relative minimum. F of C is a relative minimum. So this is f prime negative, f prime undefined, and this is f prime positive. So if the sign of f prime changes, the derivative changes from negative to positive, we get something like that at that critical point. We're going to have a relative min. So it might look like that, or it might look like this. What's the slope on that side? Well, it's decreasing, so the slope is negative. At the bottom, we have a 0 slope. On the right, we've got a positive slope, so the derivative is positive. So if we go from negative to positive in our slopes, negative to positive this way or negative to positive this way, we get a relative min, because we're going to be at the bottom. Now if f prime changes sign from positive to negative, so maybe it's going from positive to negative, or it's going from positive to negative, in one of those two ways. So f prime is positive, that means it's increasing. Then the derivative is undefined. Then the function's decreasing, so f prime is negative. Or we've got f prime positive, so the function's increasing. Then we've got 0 slope at the top. Then f prime is negative, so it's decreasing. Well then, we're going to have a max. I don't memorize this. I literally draw pictures every time. If it goes from negative to positive and I know the slope is undefined, I draw that. If it goes from negative to positive and I know the slope is 0, I draw that. And I say, I have a relative min. And if f prime goes from positive to negative, well that means the function's going from increasing to decreasing. If it's going from increasing to decreasing in the function's derivative is undefined there. We've got a critical point due to f prime being undefined. Well, if it goes from increasing to decreasing and it's undefined, we've got a max. Or if it goes from increasing to 0 to decreasing, we've got a max. Now remember, increasing and decreasing, you want to think of those as interchangeable, with the derivative being positive and the derivative being negative. So if the derivative is positive on this side, and then the derivative is negative on that side, you'll have a max. Positive derivative to negative, we get a max. Positive derivative to negative, we get a max. Negative derivative to positive, we get a min. Negative derivative to a positive derivative, we get a min. So if f prime changes signs, you're going to get either a min or a max. And whether it goes from negative to positive or positive to negative, like that's going to determine whether it's the min or the max. Now, you might have a critical point where f prime doesn't change signs. So maybe you've got a flat spot. That was what I was trying to draw up there, unsuccessfully. Maybe it looks like this. Or maybe the graph looks like that. Tried to make it very, very obviously a flat spot there. So there's f prime of c is 0, f prime of c is 0 here. On this side, the function's increasing, so f prime is positive. On this side, the function's also increasing. So it's like it was increasing, and then it stopped increasing for just a moment, and then it continued increasing. Or maybe it's like this. The derivative is negative, and then it's 0, and then the derivative is negative again. So it's decreasing, and then it's 0, and then the derivative is negative. Well, in that case, you don't get a min or a max. You just get this little flat spot. So if f prime changes signs, you get a min or a max. And depending on which way it changes, negative to positive gives you a min, positive to negative gives you a max. Now again, I don't ever memorize these. I draw pictures every time. So let's apply this to a couple of problems. Okay, so here are the questions. We're asked to find the open intervals on which the function is increasing or decreasing. Then we're asked to apply the first derivative test to identify all relative extrema, and then we'll graph the function. Start out with an easy one. We'll just do a polynomial function. Now, in order to determine the intervals where the function's increasing or decreasing, we need to find the critical points of the function. Because the critical points, that's where the slope is 0 or the slope is undefined. That's where it could change from being increasing to decreasing, or increasing to decreasing, or vice versa. So the first thing we do is find critical points. Okay. Easy breezy. Just taking the derivative, bring the -7 down. Take the derivative of x cubed using the power rule. So you bring your power down, multiply by x to the 1 last power. 3 minus 1 is 2. Then I've got a constant times x here. The derivative of a constant times x is just my constant. And of course the derivative of a constant 3 is 0. So if we simplify this, we've got -21x squared plus 21. And remember how we find the critical points. You first compute f prime, and then you set f prime equal to 0 and solve for x. Okay, so we'll add 21x squared to both sides. Let's divide both sides by 21, and we get x squared equals 1. So we can take the square root of both sides to get x by itself. Don't forget the plus or minus on the side with the number. And we get x equals plus or minus 1. So those are critical points. We get two different critical points. X equals +1, x equals -1. Now, we have to think about this a little bit more. Those are two critical points. There may be others. Remember, critical points are x values in the domain for which the derivative is 0 or the derivative is undefined. So you have to go back to the derivative and say, are there any x values in the domain for which this is undefined? So x in the domain of f, that's notation for x being in this set called the domain of f. Are there any x in the domain, let's just say for which f prime is undefined? And no, there aren't any x values in the domain. That's a polynomial. It's nice. It's well defined for all real numbers. Okay, so we've got our two critical points, the only two critical points. Now, to determine the intervals where the function is increasing or decreasing, I'm going to call this we're going to do what's called a sign analysis. That's what I'm calling it. Let's do a sign analysis of f prime of x. So the first thing we do is we take our f prime, which was -21x squared plus 21. And you don't have to do this, but I really like to do this because it makes the computation easier. To do the sign analysis, the first thing you do is you factor f prime as much as possible. So we'll factor out the -21. -21 times x squared gives us our first term, and -21 times -1 would give us +21. And that's a difference of squares. Remember, if you're trying to factor a squared minus b squared, that's the same as a plus b times a minus b. And so my b squared here is just a 1. So I've got -21 times this. My a is x, my b is 1, so I'm adding 1 and I'm subtracting 1. Okay, so I've written my f in factored form using a special product. Might have to review this. There's going to be a lot of factoring in this chapter. Okay, so you've factored f prime, and then you want to set f prime equal to 0. Actually, we've already set f prime equal to 0 and solved for x. Those x values, your critical values, are going to be the endpoints of the interval on a number line. So let's see. We'll say next thing we want to do is draw a number line listing the critical values. And you're listing the critical values on it, critical numbers, critical values, same thing. And of course, you're putting them in order because it's a number line. It goes from -infinity to infinity. These are x values, okay? The two critical values were positive and -1, so -1 comes first, then we've got 0 in the middle, and we've got x equals 1 over here. Okay, and now we want to determine the sign of f prime on each of these intervals. So those critical values, that's where the derivative is 0. If the derivative is 0 here, that's where it could go from positive to negative, or the derivative could go from negative to positive, or the derivative could go from positive to having a 0 slope, so it just pauses for a moment and then going positive, increasing more, or negative to 0 slope to negative. We don't know, but the places where f prime is 0, that's like a possible transition point where f prime could go from increasing to decreasing, or f could go from increasing to decreasing, or decreasing to increasing. Okay, so we've drawn a number line, and then you want to find the sign of f prime on each interval. The intervals determined by your critical values. And usually we do this using a test point on each interval. Now this is where I say to my students, you don't have to use the factored version of f prime for this. You could always just go back to the original function. I was taught to use the factored version because it's very quick and easy. So I'm trying to find the sign of f prime, and f prime is this times this times this. So I'm going to put f prime up here, and I want to say f prime is the product of -21 and x plus 1 and x minus 1. So I'm listing the factors of f prime below the number line. Okay, now watch this. On each interval, you want to pick an x value. Since the derivative is 0 here and here, on this interval, it's either positive the whole time or it's negative the whole time. And if you're saying to yourself, how do you know, Ms. Townsend? Well, because it's only 0 here and here. So if it went from positive to negative on this interval somewhere, it would have to go through a point where the derivative was 0 or the derivative was undefined. Since these are our critical values, and the derivative is 0 here and here, it has to go smoothly through those values. So yeah, the derivative can only take on one sign on that interval. It can't go from positive to negative on this interval without crossing through 0, if that makes sense. The y values on the derivative graph would have to pass through 0 to get from positive to negative, and the 0 points are already listed here. Okay, so anyway, we're trying to find the sign of each of these 3 factors on each of these 3 intervals, and these are intervals of x values, and then we're just going to multiply the signs of the factors together to get the sign of f prime. -21 is negative no matter what x is, so I'll just put negative signs there, there, and there. And then x plus 1 on the interval from -infinity to -1. Well, if I want to figure out the sign of s plus 1, I just pick out an x value on this interval from -infinity to -1, and I plug it in here. So you just try, say x equals -2, substitute that in there. At x equals -2, x plus 1 would be -2 plus 1, so that's -1, so that's negative. And x minus 1 is -2 minus 1, it's -3, so that's negative. Now, normally I do not write this step out. The whole reason we do it in this factored form is to be able to do this plugging in the x value in our head. It's really simple. But I wanted to show you here in this video so that you know exactly what I'm doing. I just plug in x equals -2. -2 plus 1 is -1, it's negative. -2 minus 1 is -3, that's negative. Then on the next interval, you want to pick an x value. Any x value you want, it just has to be between -1 and 1. So let's try x equals 0, because it's the easiest to evaluate. 0 plus 1 is positive 1, and 0 minus 1, if I plug in 0 for x here, is negative 1. Again, normally I don't write this down. I just do 0 plus 1 is positive, 0 minus 1 is negative 1, which is negative. Okay, I forgot to multiply the signs. So we found the sign of each of the factors, and then you multiply these together. So f prime is a negative times a negative times a negative on this interval. Negative times negative is a positive. Positive times negative is a negative. So f prime is negative over there. Okay, on the interval from negative 1 to 1, what do we get? Well, we have a negative times a positive times a negative. Negatives cancel in pairs, so this is positive. And then on the last interval from 1 to infinity, pick an x value. So when x is 2, I get 2 plus 1, which is, of course, 3, which is positive, and 2 minus 1, which is 1, which is positive. So we have a negative times a positive, which is a negative. Okay, so we found the sign of f prime on each interval by listing the factors of f prime below the number line, then substituting a test value into each factor, and then determining the sign. So you're determining the sign of the factor, and then multiply the signs together, or sometimes we might have a quotient here. You might divide the signs as well. But the conventions are the same. Positive times positive is positive. Positive divided by positive is positive. All of those rules still work. So we substituted a test value into each factor to determine the sign, and then multiply the signs to find the sign of f prime. Now this seems involved, but it's actually not too bad once you get the hang of it. It just takes a little bit of practice. So we've got f prime here, and now we've got this chart. Now the first question said, find the intervals on which the function is increasing and decreasing, and we have. F prime is decreasing whenever the derivative is negative. So the function is decreasing over here, and it's decreasing over there. And where is it increasing? Well, it's increasing over here. Now again, when they ask you that question, find the open intervals where the function's increasing or decreasing, they're asking for an interval of x values. You're going to use the x values shown on this number line. So the function's decreasing over here, so maybe it looks like that. And then it has 0 slope, and then it's increasing. Then it has 0 slope, and then it's decreasing. I don't actually know what the graph looks like, but that's the rough idea. It's decreasing, 0 slope, increasing, increasing, 0 slope, decreasing. Okay, so where is it increasing? It's increasing on this interval right here. The endpoints of the interval are -1 and 1. And it's decreasing on 2 intervals, this one and that one, that goes all the way from negative infinity to -1 if we're going from the far left. You don't have to write negative infinity and positive infinity there. Normally the arrows indicate that, but I find a lot of Calculus 1 students benefit from writing that. It just helps them to see. You're just reading this from left to right, negative infinity to -1. It's one interval where it's decreasing, and it's also decreasing on 1 to infinity. Okay, so that was the answer to the first question. Now the second question said, apply the first derivative test to find or identify the relative extrema. Well, I kind of just did. If it goes from decreasing to 0 slope to increasing, well, that's obviously a min. So f of -1, which happens to be -7 times -1 cubed plus 21 times -1 plus 3, when I substitute back into the original function, it's -7 times -1 minus 21 plus 3. or that's 7 plus 3 is 10, 10 minus 21 is negative 11. That is, according to this, a relative minimum by the first derivative test, because it goes from decreasing to zero slope to increasing. Okay, what about f of 1? Well, it goes from increasing to zero slope to decreasing, so you're going to have a relative max at 1. So f of 1, that's negative 7 times 1 cubed plus 21 times 1 plus 3. So that's negative 7 plus 21 plus 3. So we get 17. That is a relative max by the first derivative test. And then the last thing that we were asked to do was to graph the function. Now I don't have a lot of details, but I know a relative min and a relative max, and I can also find pretty quickly the y-intercept, because we know the y-intercept is where our graph crosses the y-axis, and on the y-axis x equals 0, because this is x equals negative 1, and x equals positive 1, x equals 2, and x equals negative 2. So what is x equal to on this line? 0. When x is 0, y is 3. And what else did we learn? At negative 1, y is negative 11. So this is not to scale, negative 11. And at 1, f is 17. Also not to scale, 17. And it's decreasing, then we have a 0 slope, then it's increasing, then we have a 0 slope, and then it's decreasing again. So I think what this is saying, and I don't know where it's crossing the x-axis, but I think this is saying we get something like this. Actually, if you studied polynomial functions, I've got a cubic polynomial, and it's multiplied by a negative 7, so the end behavior, it looks like x cubed, but it's sort of flipped the other way. It starts positive and it ends negative. It rises over here and it falls over there. Now that's a negative first derivative because it's decreasing, 0 slope, so we get a relative min. 0 slope, and then it's increasing, so going from negative slope to 0 slope to positive slope, we get a min. Or if we go from positive slope to 0 slope to negative slope, we get a max. So that's the first derivative test. So our relative max is right there. It's a relative max of 17, and it occurs at x equals 1. And this is a relative min of negative 11, and it occurs at x equals negative 1. Okay, we don't have enough time in this video to do another example, but in the next video I'll do more advanced examples. If you already have the idea, you do not have to watch more videos. You can go ahead and get started on the homework, but in the next few videos we're going to do more advanced problems. So we'll have a quotient, we'll have a cube root, we'll have a trig function, and we'll see how these principles play out with more interesting functions than the ones we talked about. I've even got this exponential function, which is kind of cool. So that will be the next video.